We created the Sunulator to help people answer the question, is solar worth it?
Hi, I'm Andrew Redaway from the Alternative Technology Association. This video is on Sunulator, our free solar feasibility calculator. And as part of a series, there's a few that I've already recorded, and we're now looking at running Sunulator after we've already entered in quite a lot of information on the electricity consumption, tariffs from the grid, the solar system and battery, and costs. And we're now ready to click the button. But just before we do, there's one little section up here. This lists the scenarios that Sunulator is going to run. It'll run all of them in turn, unless we tell it to ignore one or two. Normally you wouldn't enter anything in here, but if you did want to ignore, then one of the scenarios, and you just click yes. You might want to do that if you change a few values and you want to rerun it, but one of them's not relevant. And if you've got a slow computer, then it can help to speed it up if you only run one or two scenarios. So let's click Sunulator, and I'll explain what's happening as we go along. Okay, so it's warning us it'll take several minutes. It's a good idea to close any other Excel spreadsheets while Sunulator is running. And this is basically a standard disclaimer. If you make economic decisions based on Sunulator, then please don't come back and try and make claims on the ATA. Alright, so I've clicked OK on those messages. It's now running, and if we move down to the bottom left of the screen, we get some little messages here on what Sunulator's doing. So at the moment it's just setting up the Sunulator simulation run, and it's called a simulation because it's taking a simulation approach where it's stepping forward through the 1 year of history that we've entered in, the consumption history, in half-hourly intervals. So if our consumption history extended over a whole year, which is the best idea, then it's going to be looking at 365 times 48 intervals for each scenario. So that's 4 scenarios, including the business as usual. And in each interval, what it does is it first looks at, well, what's your consumption in that interval. So maybe, I don't know, 0.5 kilowatt hours. What's your generation in that interval? Maybe 1 kilowatt hour in that half-hour interval. So it then does a netting off and says, well, you've got your generation is exceeding your consumption, so you've got some excess solar generation. If we have a battery, then it will look at whether the battery's full or not, and what the rules are that you've, and any restrictions you've placed on the battery charging, and it will decide whether or not to put that half a kilowatt hour of excess solar generation into the battery. If not, it will export that out to the grid. So it's done that energy netting off to work out what's happening, and then after that it looks at the dollar side. So it will say, well, all right, in that half hour you're exporting half a kilowatt hour out to the grid. Your feed-in tariff is, say, 6 cents. So in that half hour you've earned 3 cents. And so that will make a contribution onto your annual electricity bill. And it goes through the whole year taking that approach. So the advantage of a simulation approach is that it's it's as realistic as we can get it. There are some other calculators that just work off like an average day. So you have an average solar generation curve and you have an average consumption curve, and it just assumes that you have like a groundhog day. It's just repeating the same day 365 times. The problem with that is that you come up with unrealistic results. In reality, you're going to have some sunny days, some cloudy days, some days that are sunny in the afternoon, cloudy in the evening, vice versa. You're going to have days with high consumption, days with low electricity consumption, days when you're on holiday, and there's a lot of variability in both the generation and the consumption. And in general, the more the variability, the less favourable it is for your economics for a solar project or a solar battery project. For example, if you've got a battery, then there'll be some days when you don't have enough excess solar generation to fully charge the battery. So that means you're not going to get a full cycle out of the battery on that day. Then there'll be other days when you have enough solar generation to fully charge the battery up, but you don't have enough consumption in the afternoon and evening and night time to fully discharge the battery. So again, you haven't got a full cycle out of the battery on that day. And the next day, following on from that, you've started with a partially charged battery. So again, you're not going to be able to get a full cycle on the next day either. So if you'd gone with like an average generation day and an average consumption day and repeated 365 times, then that might have shown a full cycle out of the battery, 5 kilowatt hour charge and discharge, for example, if it was a 5 kilowatt hour usable battery. But that would be unrealistic. In the real world conditions, you might have, some days you might have charged and discharged 5 kilowatt hours, but other days you might have only discharged 2 kilowatt hours, or if you're away on holidays, for example, then over that period you might have only discharged half a kilowatt hour out of your battery just to power the fridge at night. So that's why a simulation approach is really the accurate way to work out what results you're going to get from a solar system and a battery system. Okay, so Sunulator's finished, and it's popped up this quick results sheet. So this just gives us some quick notes on what's come out of the simulation for the different scenarios. After we click OK on this, it'll take us to the results section, which we can go into more detail, more statistics, more charts, that type of thing. But I'll be covering that in the next video. So the first thing it tells us is just a note on the carbon dioxide emissions. So an environmental point of view. So the 4 kilowatt solar system has given us the greatest benefit, and I'm not sure how many tons of carbon dioxide that is. It'll show us in the stats sheet, but it's equivalent to removing about 2 cars off the road, just assuming standard driving kilometers and standard petrol consumption, etc. You may wonder why the two battery systems are not quite equal. It's allowed for some losses in the battery. So with the losses in the battery allowed for, then the carbon benefit would be slightly less than the solar system with no battery. Okay, the next section is looking at self-consumption of solar generation. So that's saying, well, how much of the solar electricity has been used on site compared to being exported out to the grid. And in this case it's the one with the 5 kilowatt hour battery, the big battery, which has the highest self-consumption. 65% is still not very high, so still 35% of that solar generation is getting exported out to the grid. It'll be interesting to look at that in a bit more detail in the statistics sheet. And the highest battery utilization is the one with the small battery, 97%. That's quite a high number. So with a smaller battery, then you're more likely to be able to charge it up and discharge it every day, which is what the utilization number means. That's a statistic that we've invented at the Alternative Technology Association to help understand the economics of battery systems, and it's just the average discharge out of the battery over a whole year as a percentage of its usable capacity. And then we get some financial stats down the bottom. So for the electricity consumer, it's a household in this case. The greatest net present value and the fastest payback period both occur with the solar system with no battery. So net present value of $3,015. I'll explain that in more detail in the results area, but it's basically considering all of the bill savings out for 20 years and also the costs that you incur, like the replacement of the inverter and that, and wraps it all up into one number of like what's the overall value of this project, installing this solar system in today's dollars. So it's positive, which is a good thing. And the payback period of 10 years, is that favourable or not? I would say 10 years is still pretty favourable. So you're getting a payback on your investment. You've recouped your upfront costs before the inverter has needed to be replaced. So that's a good thing. And 10-year paybacks, so some people would look at that and think, oh, that's actually pretty long, and that doesn't look very attractive. But we'll see in the results section, if you convert that into a internal rate of return, like a equivalent interest rate, it works out about as attractive as a financial investment, with a interest rate of I think it's maybe 7% or something, which is certainly a lot better than what you can get at banks at the moment, and it's tax-free, any bill savings that you get on your electricity. So yeah, from these quick results, it looks like the solar system with no battery may be a good way to go. Alright, that's it for this video. Thanks for watching.